We have another example here. We have a 3-meter diameter merry-go-round with a rotational inertia of 880 kilogram meter squared. A child with mass 35 kilograms standing on the edge of the merry-go-round as it rotates at 15 RPM. If the child quickly jumps off, heading straight out from the center, what is the new rotation rate, angular speed, of the merry-go-round? Treat the child as a point mass. So I have a picture of a merry-go-round here in case you don't remember what it is or don't know what it is. They're not very common on playgrounds anymore, which is sad. Anyway, we have two objects that we're dealing with here. We have our merry-go-round. I'm going to just call that object 1. We're told that the rotational inertia, which means moment of inertia, of this merry-go-round is 880 kilogram meter squared. We're also told the diameter is 3, which means the radius is half of that, 1.5. Object 2 is the child. We're told the child has a mass of 35 kilograms. The child is originally on the edge of this merry-go-round. The system with this child on it is originally rotating at 15 RPM, so revolutions per minute. The child's going to jump off, heading straight out from the center. That's actually an important piece of information. And we're trying to find this final rotation rate. Now, in terms of this falls under the category of what we would call an explosion. It's not really an explosion in our everyday, our normal usage of the word, but the child was originally on the merry-go-round and now they're not. So we have two objects that were rotating together and now they're not, which in turn affects the rotation rate of the merry-go-round. That means the initial angular momentum of this system initially still has to be angular momentum finally. Okay. Because they're telling us to treat the child as a point mass, we're saying the child is essentially just this point, a small object compared to how far away they are from the center. Now, the reason why jumping straight out from the center is important is because let me draw this from above. If we were looking down on the merry-go-round, the lever arm vector, essentially, R, would point from the center of the merry-go-round out to the child. But the child is going straight out. This is their velocity. So the child, by jumping straight out, is not applying a torque to the system. They're not applying a torque to the disc, to the merry-go-round itself. And so there's no torque due to the child. When the mass, if we're talking about the mass being concentrated, this point mass, we can say the angular momentum is simply R crossed with the linear momentum. But linear momentum is mv, so if I were to put an m by my velocity, that's my linear momentum. By saying the child jumps straight out, we're saying that the final angular momentum of the child is 0. The child has no motion that is perpendicular to R. This is a cross product equation, just like torque. For a point mass, we can write this as the magnitude of those two vectors times the sine of the angle between them. The angle between those two vectors is 0 degrees. Sine of 0 is 0. So what this is defining for us is that the child has no angular momentum relative to this rotation axis after they jump off. So that means initially is the two of them together. Finally is just the merry-go-round. Okay, so to write this, since they're rotating together, let's see, we could say I1 omega 1 initial plus I2 omega 2 initial, but because they're on the same thing, we can just call these an omega initial and say that I1 plus I2 is the total moment of inertia of the system times that initial rotation rate has to equal I1 omega final. The kid has jumped off. The child has no angular momentum because of how they jumped off. And so finally, it is only the merry-go-round that has that angular momentum. And that omega final is what we are looking for. So omega final will be I1 plus I2 over I1 times this omega initial. Now they gave us I1, 880. So we need to figure out I2. They gave us the 15 RPM. That will be our omega initial. I2, I of the child, a point mass simply means the mass is concentrated such that we're treating it as if it were all the same distance from the rotation axis. The point mass is the same as a hoop or ring. And so we simply need the child's mass times how far they are from the rotation axis. Well, they told us the child's standing on the edge, so we can put them at that 1.5 meters. To find their I value. Now I am leaving omega initial in terms of RPM, which means omega final will be in RPM as well. If you're unsure of whether or not you can do that, go ahead and convert to radians per second, and that would be fine. Okay, so I'm getting 16 RPM. So the merry-go-round is rotating a little bit faster than it was before because this child has jumped off. Which hopefully makes sense. We now have less mass than we started with. So hopefully we can see that it should rotate faster. Now, I do want to make one side note because I always see students doing something like this. I have given a problem like this before, and what I've seen done is students will take the 880 to find the mass of the merry-go-round, and then to add the child back on, they find essentially an M1. But then they come back and say 1/2 M1 plus M2 R squared to be the total moment of inertia of the child and the merry-go-round together. This is not valid. This would imply the child is uniformly distributed over the entire surface of the merry-go-round, which is kind of silly. We cannot add the masses together unless the mass is distributed the same way for both objects. We can, as we did in the problem, add their I-values. That's totally valid. We can add the individual I-values of the merry-go-round and the child. That's not a problem at all. Do not try to add masses when the objects are not the same size and shape. So there's no need to find the mass of the merry-go-round in this case, which we saw as I solved through the problem. Just be thoughtful in terms of thinking about how mass is distributed in terms of I.